we have studied some examples of cylindrical symmetry, how to calculate the magnetic field under that kind of symmetry. Now, another kind of symmetry is planar symmetry. Okay, planar symmetry. So we're going to look at an example of planar symmetry. How do you think of a planar symmetry case where the current distribution has planar symmetry? Well, imagine I have an infinitely large sheet. Okay, infinitely large sheet. It doesn't carry a uniform charge. Rather, there is a uniform current flowing through it. Okay, flowing on its surface, I should say, flowing on its surface. And it's uniform, which means if I draw on the x-axis, okay, then the current density along the x-axis should be the same, which means if you look at a certain displacement along the axis from here to there, let's say, from here to there, we call it dx. How much current is flowing between here and there within dx? We call it di. Okay, di over dx, which we call j, is a constant, independent of x. Okay, so that is why we say it's a uniformly distributed current on the surface of that sheet. Okay, and we want to know is how does one calculate the magnetic field above and below that sheet of current? Okay, now in principle, you know how to do this without even using Ampere's law. What you can do is, okay, divide this infinitely large current sheet into a whole bunch of parallel currents, right? Each one is infinitely long, right? Each one has a current di over a distance dx, and so you have an infinitely long wire, right? For that wire, can you figure out the magnetic field produced by that wire for a point somewhere here? Yes, you can, right? You get dB, right? And then what you do, you can add contribution of all these wires together. You can do that, okay? Now, this can be done, but you have to do it with integration. Okay, it's not as straightforward as as a very simple calculation. The advantage of Ampere's law, of course, is to allow us to figure out problems like that, with high symmetry in a current distribution with greater ease. And that is what we wish to achieve. So let us take a look at this distribution from this angle. Okay, so I'm looking at, I'm going to follow the direction of the current. So I see a sheet like this. Okay, so the sheet which is the xy plane is now oriented like that. Okay, so I'm looking at it like this. What I see is a whole bunch of current flowing in, right? Just like, follow my eye in this direction and see a whole bunch of current flowing in. Okay, now it is clear that this very uniform distribution of current will exhibit some sort of symmetry, which is reflected in the distribution of the magnetic field lines. What is the orientation? What is the direction of the magnetic field line at this point? We need to find that first. Okay, we need to find that first. How do we do that? Well, there is a horizontal direction and there's a vertical direction. First of all, let's argue that it is impossible, okay, for the magnetic field line to be in the vertical direction, either up or down. That is simply not possible. Okay? Why is that? Because if it points upward like this, okay, or it has an upward component like this, then what happens on a symmetrical point below the plane? Okay? On a symmetrical point below the plane, if there's an if here it points like, there is an upward component like that, and over there symmetrically you have an downward component like that, right? And what is wrong with that? Okay, here's what's wrong with that. Suppose then you draw a box, not a loop, but a box. Okay, a box. Then guess what? On the surface of this box and on that surface of the box, you have a net magnetic flux going out and a net magnetic flux going out, right? And what is wrong with that? Well, you will get a net magnetic flux over this box. Guess what you just found if that were the case? You would have captured some magnetic monopole, okay? The magnetic flux over self-enclosed Gaussian surface then wouldn't be zero. That is only possible if there's a magnetic monopole, which of course is not the case here. You just see a bunch of current, that's all. So it is impossible to have a vertical component, either up or down. So that means the magnetic field can either point only this way or that way. Okay, that is clear. So the question is, which way is it? Okay, which way is it? Well, take a look at this current, for example. This current produces a magnetic field like this. All these currents pretty much produce a magnetic field pointing like this, so you can understand easily that the magnetic field lines right above, somewhere above the plane of the current should point like this. Okay, and below the plane should point like that, right? That's how it turns around like that. Okay, there are other ways to argue why this current, this magnetic field can only point parallel to the surface of the plane, but not perpendicular to it. There is no perpendicular component. You can also use other symmetry arguments to not just the non-existence of the magnetic monopole, but other arguments. I'm going to leave that argument to you. Okay, but anyhow, now that we know the field line can only point this way, and the field line over there can only point that way, we are going to construct an Amperian loop to capture the symmetry of the problem. Okay, because of the symmetry, it's an infinitely large uniform, right? So if you look at a point P, you draw a line parallel to the plane, passing through point P. Everywhere on that line, because it's the same distance to the sheet, right? To the plane, right? The magnetic field should have the same magnitude, right? And they all point in the same direction. Over here, same thing. Suppose I draw another line below the plane and make sure, if I make sure that this distance equals that distance, we call it d, okay? Then by symmetry, the magnetic field lines here should point backwards, should have the same exact magnitude as that. Okay? So, what kind of Amperian loop should I draw? Well, I'm going to draw a straight line segment and a straight line segment to capture the symmetry, right? Because that's what field line is oriented. But how do I self-enclose this loop? Well, I'm going to cut a vertical line here, another vertical line there. Why? Because as you move vertically, you are moving in a direction that is perpendicular to the magnetic field. Remember, the magnetic field anywhere above that plane should always point to the left. Anywhere below the plane should always point to the right. Okay, so there is no contribution to B dot ds from here and from here. You only get from the top and the bottom. Okay, now that makes things really simple. Suppose the length from here to there is L, and from here to there is also L. Okay, after all, this is a rectangle. Then I can write this. I can write B dot ds for the contour 1, 2, 3, 4. Forget about 2 and 4. Okay, only 1 and 3. From here to there, let's look at the top first. Okay, from here to in the top first, we call it 1, segment 1 from here to there. In segment 1, B dot ds, and here is segment 2. So here's 1, 2, 3, and 4. Forget about 2 and 4. They don't contribute to the integral. B dot ds. But in segment 1, right, B and ds aren't they in the same direction? So I can write B ds. That's it for segment 1. Similarly, segment 3, B and ds both point to the right. B ds. And also, by symmetry, B throughout the entire segment 1 has the same magnitude. Okay, I'm going to take that out. B segment 1 ds integral plus similarly B segment 3 ds. Now even these two b's are the same because I deliberately made this distance equal to that distance. Okay, so what do you think that is? Isn't that the total length from here to there, which I call L? Same thing, from here to there, length is L. So this is just 2BL. Okay, what do you think that should be equal to? That should be equal to mu naught times I enclosed. That's what Ampere's law tells me, right? And mu naught, I'm going to copy. What's I enclosed? It is the current enclosed by this loop, which is from here to there. How long is that segment from here to there? That's L. The length is L because it's the same as this and same as that. And remember, the current per unit length along the x direction, along this x direction, is J, right? Per unit length is di over dx is J. So you have a total length of L. What is the total amount of current that you enclose from here to there? Isn't that J times L? Right? Okay, now we can cross out the L on the two sides. Then I get B equals 1/2 mu naught J See how simple that is. Okay, the magnetic field both above and below turns out should have a uniform magnitude everywhere in space. 1/2 mu naught times J is directly proportional to the current density per unit length, J. This would be a nasty three-dimensional integral problem if you try to integrate over all these current elements. But what we did here, by picking up a rectangular ampere loop, we could solve this problem with great ease. And so that is an example of planar symmetry. Okay, so let's see. How many symmetries have we discussed so far for application of Ampere's law? We discussed cylindrical symmetry and planar symmetry. Is there anything else? What's missing? Well, in the case of electric field, we also discussed what? Spherical symmetry, right? Okay. Can we do the same thing here? Can you think of a current distribution that is spherically symmetrical? Now that is quite a challenge, okay? Think about it. Can you find a distribution of current such that the magnetic field exhibits some sort of spherical symmetry? Well, you can think of a case of a current flows out radially from a certain source, but that is weird because that would mean something is coming from that. It's like a radioactive source of something. But in reality, current form loops, right? They don't really start from a certain point. They form loops. So we're not going to worry about spherical symmetry when it comes to magnetic fields. Okay, only planar and cylindrical symmetry. Now, another thing I want to discuss with you is how come the B field does not depend on the distance d? Okay, remember in the case of electric field, we have a uniformly charged infinitely large plane. The electric field there also was independent of the distance, right, to the plane. In fact, you recall that was E was equal to what? Sigma over 2 epsilon naught. Remember that? Sigma over 2 epsilon naught. We have a very similar situation here, mu naught J over 2. And again, I want you to pay attention to the symmetry of the two cases. 1/2 and 1/2, they're both here. Replace 1 over epsilon naught with mu naught, and replace the surface charge density sigma with the current density J, and you go from E to B. See how simple that is, the analogy between the two. Okay, and how did we argue that the electric field there should not be dependent on the distance of a point to the sheet which contains the charge? Well, we used a dimensional argument. Remember that? What did we say? We said, first of all, E should be proportional to sigma, and sigma itself already contains all the right dimensions besides epsilon naught, because it's charge over length squared. Okay, that's in Coulomb's law. That's how you get the electric field. So there is no other place in the formula for D to appear. Okay, otherwise you're going to break the dimension. Now, can we do a similar argument here? Can we do a similar argument here? The dimension of the magnetic field, we know it's always mu naught times the current divided by some sort of length. Okay, here you have mu naught. What about J? J already has the right dimension. It is current over distance. See, current over distance. So, mu naught times J, this combination gives you already the correct dimension for the magnetic field. And therefore, this distance D cannot possibly be anywhere in the equation, because if you put it somewhere in the equation, you are going to break the correct dimension. So therefore, D should not belong in the magnetic field. Therefore, above and below an infinitely large sheet of conducting current is independent of that distance of any point to that sheet. Okay, so it's a similar argument here.